Okay, good morning, everyone. Welcome to class. So let's talk about moment and variance. Now let's recall what we have discussed the last time. We were talking about expectations of a random variable. And in case you've forgotten what expectations are, they're the averages of the probability mass function. And the probability mass function is just the continuous version, not the continuous version, the limiting object of a histogram. So we were studying a few properties of the expectation, including what happens if I add a constant shift to the distribution. For example, you have a midterm score, you have a histogram, I give everyone 10 points, right? Then I'm not changing the distribution, I'm just shifting it to the left. Okay? So the probability mass function will not go up, it always goes to the left and the right. And so in terms of the expectation, if you have a constant c, you're going to add it to the original the expectation. I've also shown you another example where I say that let's multiply everyone's score by 1.5, which is another constant. And it turns out that the new expectation would just be the new constant times the original expectation. Again, the PMF doesn't go up, it just gets spread out or shift. What I want to do today is to tell you a little bit more general operations of the expectation. And here is the theorem that I want to comment on. The theorem goes as follows. Let's say I have a random variable x, and then I have a function g. Okay, I have a function g. This function can be any function. And I apply the expectation to this transformed variable x, which is gx now, then this expectation can be written as the summation of this gx times the px. P is the PMF. So let me give you an example. If you're looking at a random variable x, and I want to calculate the expectation of x squared, then you're going to look at expectation x squared equals to summation x squared times p of x. Okay? If you're looking at expectation of 1 over x, that's going to be the summation of over x and px, and the thing that will be here will be 1 over x. And if I want to use cosine of x, then it has to be the summation of cosine of x, p of x. This theorem tells you a lot about the property of expectation. In particular, when you have a function something like this, it is not the same as the expectation, 1 over the expectation. And I can tell you again, over the semesters, every semester we have mistakes like that. For example, if I calculate the average of a Gaussian distribution, I calculate some average, normal distributed, let's say your midterm scores, and then I say, well, okay, what would be the, if I take the 1 over, take the reciprocal of that random variable, what will happen to your average? And then and a lot of students will say, oh, 1 over the average. No, okay? If you take 1 over the random variable, you're taking the expectation for 1 over x. That's not the same as if you're taking 1 over the expectation of x. Any nonlinear operator does not translate in the expectation. The expectation is a linear operator. So why is it true? Why is this theorem true? Here is a pictorial illustration. If you understand this picture, you're good to go with the expectation or the properties. So on the x-axis, you have the original probability mass. So in this case, I have 4 states, 1, 2, 3, and 4. They have different heights. And then here I have a function, it's called gx. It's going to take the random variable x, I'm going to map it to a new variable called y equals to gx. Then what will happen to this new random variable? Now there are 2 things to look at. One is the locations or the state of the new random variable y, okay, the state. The other thing is the probability mass, which is the height of the probability. These 2 things will have a different behavior. According to this diagram, your impulse, this impulse, will be mapped to a new location. See that? Because of the mapping, because of this nonlinear curve here, it will be mapped to a new location. However, the height of this arrow is not changed. So let's say this is x1. This will become this will become g of x1. This is x2. This is g of x2. The height of each probability mass will remain as px. And here it will just be the same px. It wouldn't change. And so if you calculate expectation on the x-axis, it will be the probability of x times, it will be the sum of x times the probability of x, which will be the original equation. If you go along the y-axis, it will be g of x times the height, which is px, and then sum over all the possible cases. Then sort of explain the right-hand side of this equation. You have this g, which is the new location, times px, which is the same height. The height is not changed. So this is the property of this random variable, and then you apply any transformation to the x. And this applies to whatever transformation you can think of. It can be linear, nonlinear, going up, going down, whatever, that will apply. Another property, which is also very useful, is a summation of two different functions. You have gx and you have hx. Now, do not get confused as we are moving to talk about two different random variables. As we go to chapter 5, we talk about random variable x and random variable y. They each have a different distribution. And here, the underlying randomness remains the same. It is gx and hx. It's not gx and hy. Okay? So this is gx and hx. They have the same underlying randomness. And it turns out that if you take the expectation of gx plus hx, you're going to get expectation of gx and the expectation of hx. Now, if you want to look at the example, think about this example. You have x, and then you have a constant c. The c will come out because of this theorem. You have expectation of x plus c. Okay, this theorem doesn't come from the previous one. The previous one is a functional transform on the random variable x. This one deals with this addition of two functions. So why is this true? Well, if you want to prove, the proof goes as follows. You have gx plus hx, and then you have you have this px. Px, your probability mass. You sum over all the possible x. Then, because this is a summation, that should be decomposed into two parts. So you have summation gx and px, and then you have hx and px. Sum over all the x. And this is the expectation of gx. This is the expectation of hx. So it's very easy to show this result. And you can see that if I have a problem like this, I have an offset, it's very easy to calculate. So these are the two properties. And together with the scaling property, which I mentioned last time, when you have a constant c multiplied with a random variable x, the c is going to come out, and then it's going to multiply with the expectation of x. Now, the picture here is that you're shifting the pulses to a new location, and you're not shifting the entire chunk of pulses to the left or to the right. You are making the spacing between the pulses bigger or smaller, depending on whether your c is bigger than 1 or smaller than 1. Okay? So here is an example. Let's say you start with 0, 1, and 2, and then my constant is 3. Then I'm going to move the 0 to 0, but 1 to 3, and 2 to 6. So the spacing between the two pulses, they are widened. The DC shift operation is also easy to understand. You take the entire chunk of PMF, you move to the left, to the right, and so the mean will also go up by the proportion. So let's say you have x plus c, then c will come out added to the expectation. So that's the property of the expectation of x. You have 4 properties. Are these good? Okay. Cool. Now, let me talk about a little bit variation of this concept of applying a function to the random variable. Now, later on, when we go to chapter 4, we'll have another whole section about a transformation of a random variable, a functional transformation of random variables. In that case, we're going to look at a lot more complicated things. We're going to derive the new PMF, or we're going to derive the new PDF of the random variable. Here, we're only looking at the expectation. Now, the difference between deriving the new PMF and deriving the new expectation is that deriving the expectation is 10 times easier. Why? If I want to derive the new PMF, I give you a function, let's say psi of a random variable x. I tell you the distribution of x. Then you need to look at the new location, and then you need to go, the PMF, the height will stay the same, but then the location will become different. And so you need to mess up all these calculations, find the PMF. For the expectation, all you need to calculate is just the average. You look at the original average, you calculate the new average. Done, just one number. Okay, so just bear in mind that we're going to look at this transformation of random variables multiple times. This is just the case where we're looking at the expectation, a single number. So what should we talk about here? I want to introduce a concept moment. Moments are very easy transformations. You take the random variable x, you take it to the power k. That's it. Now, how do we define this? Well, if you have the random variable x, if you take it to the power k, you take the expectation according to our theorem, it is just going to be x to the power k times px, and then you sum everyone up, period. As simple as that. So if you take k equals to 1, what do you get? You get expectation. K equals to 2, you get something more relevant to a concept called the variance or standard deviation. Take k to the 3, you get another statistic, okay, which is called a skewness. Take k equals to 4, you get something related to a thing called a kurtosis. Okay, it's getting something like that along that line. So that's the concept here. X to the power k, kth moment. Okay, so now what is x to the power 0? X to the power 0 is 1. It's a constant 1. Okay. All right, so let's go to this example. I flip the coin 3 times, and then as a fair coin, I let x be the number of heads. I tell you the PMF. The PMF has 4 states, 0, 1, 2, 3. Their probability masses are 1/8, 3/8, 3/8, and 1/8. I ask, what is the second moment? X squared. X squared. Okay, formula is here. Let's just plug it in and see what it is. So expectation of x squared is, okay, so there are 2 choices. Okay, one is, of course you have 0, and then you have 1/8. Should I take 0 squared times 1/8, or should I take 0 times 1/8 squared? Of course, there's something else, right? There's a 0, there's a 1/8. Would it be 0 squared times 1/8, or should it be 0 times 1/8 squared? 0 squared. Okay, it's here. So here will be 1 times 3/8. The square should be with 1. And then I have 2. The square should go with 2. Then I have 3. Square should go with 3. Never put your square with the 1 over a, 3 over a, 3 over a, and 1 over a. Again, every semester where students putting the square there. Don't do that. Okay, so the P and F is never changed. You always just change the state value. Okay, so what do we have here? So this is 0, this is 3 over 8, this is 12 over 8, this is 9 over 8. And so we have, what is this? This is 24 over 8, so you get 3. So we find the expectation of this x squared. Does it have any meaning? Well, the meaning will come very soon as we talk about the concept of variance. So the variance is defined as this. You have a random variable x, and then you have a constant called mu, or mu x. This mu is the expectation of x. Then you take the square of the difference, you take the expectation. That's defined as the variance. Now, we can always just plug in a formula and then derive things. But let's see what is the physical meaning of this equation. The physical meaning of this equation. Now, we know the physical meaning of the expectation of x, right? So you have the PMF, you have the height, and then you have the state value. You just take this weighted average. And then you find sort of the midpoint of your distribution. Not exactly the midpoint, okay? It's sort of the middle of the distribution. What is the variance? What is being captured by the variance? Let's say I have a histogram. This is my histogram. What is being captured by the variance? Standard deviation, or whatever term you know. Yes? Okay, so measure of how varying the data is. Very close, okay, but we're missing a reference point. So when we say it's varying, how much variations are there, it should be a reference point, yes. Reference to the mean, okay? So the two of you, we got an answer, okay? So you first look at the mean, you set that as the reference point, and then you measure how much variation are there with respect to the mean. So if you have a big variance, that means your distribution will be wide. Okay, so here is the deal. This is a small. This is a large variance. This is a small variance. Okay, small variance means that you have a very small deviation, you have a very small fluctuation around the mean. So it's very concentrated. A large variance means that you're wide. Okay. So this equation means a lot of things. First of all, you take the mean. This is your reference point. Then you have your random variable x. You take the difference, you put the square. Why do we want to put the square? What happens if I do not put the square? Yes. Right. Do you guys hear that? Because if you do not put the square, you have positive, you're negative. You don't even know how to measure the deviation. Right? You just know it will be assigned value. So you put the square, it will become unsigned. Can we put absolute value instead of a square? Well, absolute value also measures the deviation. Can we put the absolute value over there? Now, when you put the absolute value, it's no longer called the variance. But does the absolute value version still capture the deviation? Okay, you hear that? That's the mathematician's answer, which is that squares are just 10 million times easier than absolute value. Now, if you think, how come the absolute value are so difficult? Well, take the derivative of the absolute value, and then you're going to cry. Right? Oh, absolute value. How difficult is this? Let's say you have a function like this. This is x, right? And then you have absolute of x. Take the derivative. Not too hard, right? This is 0, and this is minus 1, right? Slope minus 1, and then plus 1. This is a slope. But at this interesting point, it's not differentiable. So you got stuck. Okay, and so if you try to write a program, when you hit this 0, you just don't know what to do with it. And so in terms of the deriving theory, when you have all these non-differentiable things, you just hate it. And so squares are a lot easier. The derivative of whatever square is easy because the square will just come out, and so you get something. And so the variance is useful. And as a matter of fact, any distance function, any non-signed distance function can be used to measure this kind of spread effect. It could be this. It could be absolute value. It could be the square. It could be fourth power. If you take the third order, as long as you put the absolute value, you're fine. You can also use that. You can define whatever distance function you want, okay? But variance is defined as the square because of some laziness we have here to just use the square. It is differentiable. It helps us solve a lot of problems. Okay, so let's go back to this example. You have a coin. You want to flip it, and then it has a probability of P being a head. So it's a biased coin. I want to calculate the variance. I want to calculate the variance. Okay, so to calculate the variance, what do we need? According to this formula, we need the mean, and then from the mean, we take the square, we take the expectation again, and so on. So the expectation of x is of a binary random variable with 0 and 1, probability p and 1 minus p. What is the expected value? That's very easy, okay? It will just be 0 times 1 minus p plus 1 times p. Because you have two states, state 0 and state 1. The probability of getting state 1 is p, so p times 1. The probability of getting 0 is 1 minus p. The state is 0, so 0 times 1 is 1 minus p plus 1 times p. It turns out to be p. Easy. Okay, variance. Variance of x is, you take the expectation, you have x minus p squared, right? This is the mean. Mean is p. So x minus p squared. How do I calculate that? Oh, but then you have a square here. Oh. You just expand it. Okay, so let's expand it. So you have x squared minus 2xp plus p squared, right? So that's expansion. And then you have expected value of x squared minus 2 expected value of x times p plus p squared. Now I'm taking multiple steps into one. Here are the multiple steps. First of all, I have a minus, I have a plus, so I have 3 terms added together. And so I'm applying the second theorem I introduced earlier today to break it into smaller pieces. So I have the first part, the second part, the third part, expectation can break it into the individual pieces. So that's the first technique I used. The second technique I used is that when you have this 2xp, the 2p is a constant with respect to your x. And so they can be pulled out. There's nothing random about that. So that is property number 3. I have a scaling property that I'm applying here. And then I have a p squared. So the p squared would just be a constant, right? When you take the expectation of p squared, it just becomes a constant. So it will stay there. So now I have this term here. And then I need to calculate what? I need to calculate this expectation of x squared and then I need to calculate this expectation of x and p squared. So this I know, this is of course p, but what is the expected value of x squared? So let's do some calculation. So I have a coin flip, and then I want to calculate expected value of x squared. This thing is just the summation of, well, you don't even need to write a summation. There are only two states, right? So 0 times 1 minus p, and then 1 times 1 minus plus 1 times p. But now, since I'm looking at the square, there should be the square somewhere. Should the square be with 0, or the square should be with 1 minus p? 0, okay. So this is the second time we see this example. It should be all goes with this state. So you have p. Okay, so now let's go back to here. The variance of x is the expected value of x squared minus 2 expected value of x times p plus p squared. I know that this is p. I know that this is 2 times p, and here I have a square. So let's just group all the terms together. Then you will have p minus, this is what? This is minus 2p squared, and then I add with a p squared, so I will have minus p squared. Okay, so that will give me p times 1 minus p. And this is the variance. This is the variance of a coin flip. Now, let's see if it makes sense. Let's see if it makes sense. So, the coin flip, of course, you have two pulses. This is p, this is 1 minus p. Okay, the mean will be sort of here, which is a p, which is the proportion. Okay, which is the proportion according to your state. And then I'm measuring the variance. The variance is p times 1 minus p. P times 1 minus p. So this p times 1 minus p will sort of measure this deviation. Okay, so here is the center point. Here's the center point. Now, if my p is big, okay, so if my p is close to 1, if my p is close to 1, then make a guess whether the variance will be big or small. If my p is close to 1, the variance will be big or small? Big. It's actually small. Okay, and here's the reason. If my p is big, then what will happen to this formula is that this p is big, but then 1 minus p will be close to 0. So you have this multiplication of a big number times a small number, you get a small number. What happens to this figure is that when your p is big, then your PMF will look like this. Your PMF will look like this. And so you ask, where is the mean? The mean will be close to the state of 1. This is your mean. This is expected value of x. And then you ask, well, what is the fluctuation? What is the deviation? Well, because 99% of the time you're already there, your chance of going somewhere else is very small. Right? And so your variance will be small. You're just so close to 1. You're almost always getting 1. So where's the variance? Right? Think about this coin. Your coin is so biased that it always gives you a head. Will you still have a big variance of getting a tail? No. Your variance getting a tail will be small. Similarly, if your coin is biased towards 0, where p is close to 0, then 1 minus p is close to 1, then you just flip over this diagram that this is your expectation is close to the 0. Then you still do not fluctuate too much. So for what p that the variance will be the biggest? Half. Right? Because When the coin is a fair coin, you have the mean being 1/2, and also you have the biggest chance of fluctuating around the two sides. Right? So the variance will be maximized when you have a fair coin. As a matter of fact, if you plot this function called the variance of x as a function of p, variance of x will be p times 1 minus p. If you plot this function out, it will be a quadratic equation because this is p minus p squared. Right? So this is a quadratic equation. This quadratic equation will have a shape like this. The peak appears at 1/2, and it will be 0 when it is at 0. It will be 0 when it is at 1. So your variance will be maximized when you are at the midpoint. So as you're changing the coin, you're changing the probability for the coin flip, you're going to get different variance. The mean will always be the p, right? Of course, if your coin is more biased to have a big p, then the mean will also be a bigger p. So I want to also comment on a little bit here. So this may be interesting to you. For those who want to study communication systems, we always talk about entropy. We always talk about how much information are there in your as you're transmitting signals. When you transmit signals, do you want the signals to have a higher variance? Essentially, you want to have more. This is not a very precise statement. Okay, the higher variance actually means that you have more information carried. I want to bring this up earlier. Okay, we can compare to this discussion later on. So when a random variable, when it has a higher variance, it actually has more information. Right? Think it this way. If a random variable is always 0, is always 1, the probability of getting a 1 is always 1, you're 100% guaranteed to get this 1. The amount of information staying there will actually be less compared to a random variable that has a half a chance of getting 1 and a half chance of getting a 0. And therefore, you need to spend time really measuring that random variable. You need to take a lot of measurements to get that. Whereas, if your random variable is always giving you 1, you don't even need to run experiment because you're guaranteed to get a 1. Right? So this kind of concept is actually quite different than you think about this problem. Oh, variance, having a big variance is a good thing, a bad thing. It may mean something relevant. Depending on the problem. Now, as you can see in the previous example, calculating the variance will require you to expanding the term and then do these summations and calculations and the second movement and so on. It can be simplified with this formula here. So it says that when you have a random variable x, if you take the variance, it's the same as you take the second moment minus the first moment square. Notice that in this equation, the square is inside the expectation for the first term. Here, the square is outside the expectation. Now, this theorem is useful because instead of calculating the expansion and then doing the terms, grouping the terms, you just need to calculate the second moment, you calculate the first moment, you apply this formula, you can get the variance. And the proof of this result is very simple. You look at the variance of x, which is the expected value of x minus mu square. And so you have expected value of x squared minus 2 mu x plus mu square. So that's just expansion. And then we're sort of just repeating ourselves of the previous example. You have the expectation of x squared minus 2 mu times the expectation of x plus mu square. And since this is mu, you have expected value of x squared minus 2 mu square plus mu square. And so these two terms can cancel out each other. So you have expected value of x squared minus mu square. Mu square is just expected value of x squared. So the result is proven. The proof is exactly the same as the example we've just seen. In fact, if you don't want to remember this formula, you can always go back to the previous example, do it once. And I promise by doing it a couple of times, you will remember the proof. Not only that, you will remember the formula. And not only that, you will thank me of giving you the formula. Okay, so that's the beauty of this theorem. It's very easy to derive. Okay, so now let me talk about some properties of the variance. Here is the problem of the scaling. Okay, so you have the variance of c times x. It turns out that it will become c squared times the variance of x. So let me do this pictorial illustration for you. Here is the original PMF. You have 3 pulses, 0, 1, and 2. And then after I take this Cx, we have seen this before, 0 will map to 0, 1 will map to 3, 2 will map to 6. So it will spread out. What will happen to the variance? The variance will get bigger, but then the ratio is not just C. The ratio will become C squared. Why do you have a square of C? Why isn't it just C times the variance? Why do you have C squared times the variance? There's a very obvious reason. Yes? Exactly, because when we define the variance, there is a square. So the square has to be carried on as you calculate this variance of Cx. So it's never a C times the variance. It's always a C squared times the variance. The proof goes as follows. You have variance of Cx. So it will be the expectation of what? It will be Cx minus the expected value of Cx square. Correct? Because this is your random variable Cx. This is the expected value of your Cx. Here you will have the Cx, and then the expected value of C times x, it will just be C times mu square. And then the C, you see that there's a square. So as you group the C together, you pull things out, you're going to get C squared times the expected value of x minus mu squared. See? So that's a C squared. This is where it comes out. Oh, okay, I should move that up. Thanks. Does it make sense? Any question? Good? All right. So that's the scaling property. And then let's also talk about the DC shift. So let's say I have a random variable, and then this is the PMF, and now I am shifting the random variable x by the constant c. It turns out that the variance stays the same. It is not affected by the c. Okay? Now, unlike the expectation, the c will come out. There's no variance plus c squared. There's nothing like that. The variance will stay as variance of x. Why is that? Why is that? That should be the pictorial illustration, right? Yeah. With respect to the mean. You're just shifting. Exactly, you're just shifting, right? You're just shifting to the left, to the right. The spread of the distribution is not changed. It will remain the same. So here's the diagram. You have this, the 3 pulses PMF, and then you shift to the left by 0 to 5, so shift by 5. The variance will remain the same. You just have a different reference point. So variance not increased. As for proof, you take the variance of x plus c. So that's going to be the expected value of x plus c, right, minus the expected value of x plus c. Right? So random variable minus the mean of the random variable. And you can see that there is expectation. And here it will be x plus c minus, this is going to be mu plus c, that's a square. The mu will stay, but then the c will cancel out. And so you will have expected value of x minus mu squared. This is the variance of x. Okay, so you see that the c will be canceled out during this process. So I hope these two properties are relatively easy to visualize and understand. And so now let's go to a more practical problem, which you all understand. This is the midterm score of some students. And then if I give everyone 10 points, of course, everyone will be happy for a couple seconds because, oh, I get 10 more points. But then the second thing I tell you is that you'll be curved. What does it mean? Your grade will be relative to the position of your class. So I just move everyone up by 10 points, and I say it will be curved. Then your happiness will go up and then drop to the bottom. Because if it is curved, if it is relative position, then it's all about the variance. The variance is not changed, right? You just shift everyone to the right hand side by 10 points. Your relative position in the class remains the same. So it's a fake sense of happiness for 2 seconds. Okay, so I guess this kind of logic is very, very common in the daily sense, and we all know that. It's just that when we put it down into the equations, it becomes a lot clearer. What happens in the PMF setting, and what happens to the PMF shifting left and right and calculating the right thing. So I think that is the valuable lesson that we learned here. Now, before we move on to the next chapter, I also want to comment on one thing. The variance of a random variable x, if you take the square root, that is called the standard deviation of a random variable x. Now, that standard deviation is also not the same as the standard deviation of a histogram. You need to be very, very clear about what kind of standard deviation are you talking about. Here, whenever we talk about random variables, we're talking about the probability mass function, which is the limiting thing. When you have done infinitely many experiments, and then you calculate that PMF, that variance, and that standard deviation. If I only give you a particular experiment's empirical data that is one spontaneous instant of that experiment, you have a histogram, you have empirical average, you have an empirical standard deviation. If you have ever taken a statistics class in your AP, okay, or in another course, you will learn some P-test, T-test, Z-test, F-test, whatever, A, B, C, D, E, F, G test. Okay, so many tests that I never remember. They are different quantities. Sometimes they say that you have the population, mean. Sometimes they say you have the empirical mean. Sometimes they say you have the population standard deviation. Sometimes they say you have the samples variance. Okay, you need to be very careful of what they're talking about. Sometimes when they have this population mean, they mean the expectation. When they say they have the sample variance, it means that they're talking about the standard deviation coming from the data. And so according to different availability of the information, you need to choose different tests to test whether there is any statistical significance of your experiment. So hopefully we will have time this semester to go to those tests. Hopefully I will have a chance to clarify all these crazy tests for you. It's actually not that hard, it's just very confusing. There's just a ton of these tests. Okay, so that is the chapter on moments and variance. Any questions before I move on? Yes, please. Correct. So the variance will be called the sample variance for the histogram case. The standard deviation is called the sample standard deviation. Okay, so here is the difference. PMF and then histogram. This is expectation. Mu, sometimes we just write expectation of x. This is the average or sample mean. Sometimes people call it the population mean. That's called a sample mean. Usually the notation is x bar. And then here you have variance. This is called the sample variance. This is called the standard deviation. This is called the sample standard deviation. Now, when you go out, when you go to the internet, things will become a lot worse. Okay. They were talking about sample variance, they just say that it is variance. They were talking about sample standard deviation, they say that it is a standard deviation. And then when they do the test, they use the sample, but then somehow suddenly they will switch gear and say that, oh, assume that I know the population variance, then they will use this thing. And so that just makes all these concepts extremely convoluted and then glued together, and they're so dark that you don't understand. But once you understand the difference between these two, histogram PMF, this will converge to this when n goes to infinity, then everything becomes clear. Usually these are not known to you. These are the things that are known to you because you only have the access to the data. But in some cases, especially in the classroom setting, I give you a midterm exam. Of course, I can tell you, hey, assume that you know the population variance. Right? In practice, you only know these. And therefore, the test that you see, the statistical test, hypothesis testings, is a lot more complicated because they don't have these. Even though in the class, in the exams, it's a lot easier because you have access to those numbers. Okay, so since I only have 2 minutes, I don't want to rush into new topic. So as we come back on Friday, we will talk about random variables, different types of random variables. I hope I will have time to talk about 2 random variables, the Bernoulli random variable and the binomial random variables. Okay, so that's the plan for Friday. Thank you, everyone.